Hello everyone, welcome to the NPTEL course on scalable data science. I am Professor Shorangshu Bhattacharya from Computer Science and Engineering at IIT Kharagpur. This is lecture number 20 and today we are going to introduce the distributed machine learning. So, in the previous lectures we have already covered the big data platform, that is Spark, and we have covered various computations using the big data platform. So, in this lecture first we will cover the motivation of why distributed machine learning is important. Okay. So, we will cover two cases, one is large scale machine learning and other is edge computing, which is autonomous vehicles. But there are many examples, but these two are representative of two different types of examples. Then we will discuss an overview of the types of architectures that we can have for distributed machine learning, and then we will also cover in brief at a very high level the platform TensorFlow, which can also perform distributed machine learning, and we will see how it is different from the Spark platform, and then we will see some comparisons between these platforms. Okay, so large scale machine learning. So, as we know, big businesses collect lots of data. So, these big businesses could be in many domains. We shall see some of the domains. So, these could be in internet domain, these could be in finance domain, these could be in e-commerce domain, social networks, all these domains. Okay. And so, these data can be analyzed. So, to provide first of all insights, which is called the analytics. Okay. Then you can so insights is basically just some trends or some monitoring kind of thing. So, this is the simplest outcome that you can get by analyzing this big data. Second is patterns, which is called data mining. So, you may find some correlations between some quantities which are not trivial to understand. Then third is you can so example of pattern could be something like you may see that there is a correlation between a certain product that your company is selling and the other product that your company is selling. So, the two may be either positively correlated or negatively correlated. Okay. And then you can find predictions, you can do predictions with the lot of data that you have collected. So, this is normally called supervised learning. So, there are many examples like you can try to predict stock prices, you can try to predict the click through rate of a user, and so on and so forth. And finally, you may want to find things like anomalies or clusters or surprises in the data, which are also come in the realm of unsupervised learning, something like clustering, all these kinds of anomaly detection, etc. Now, all these companies, they have this requirement that these are these are business critical applications, and hence all this kind of processing should be fast. So, it should be over within a limited amount of time, let us say maybe 1 hour or 1 day, whatever it is, but it should be fast. So, speed is important and it should be reliable. So, the computation should happen reliably, it should not fail or something, and the processing should be flexible. So, you should be able to change. So, depending on the changing scenario of the business, you should be able to change the computation little bit without having to incur very large overhead. Okay, so some examples. So, for example, financial services industry, you could show correlations between the services purchased and the investment made. So, how much investment they are making versus what all services they are purchasing from the company. Or you could identify the customer segment, whether the customer is wealthy or not wealthy. You could recommend research article to people who are doing online trading, for example. So, you could recommend articles which will be useful for them in making decisions on online trading. Then in the e-commerce domain, you can do recommendation, like you can show people events or things that they like, or you may try to predict the click through rate or conversion rate. So, you may try to predict something like if you show a particular ad, what is the chance of this person clicking on that ad. And then you may want to do recommendation for cold start. So, people on which you do not have past data. Okay. Similarly, in the gaming industry, there are a lot of problems. For example, you could try and cluster user profiles, you could find correlations between attributes of a game and behavior, and you could try to predict churn. So, you could try to see whether a particular online gamer is leaving this particular game and going to some other game or not. Similarly, in healthcare. So, these are so as you can see, there are lots and lots of industries with large amounts of data. So, this data is collected from the user, and basically doing machine learning, large scale machine learning is a very important business for all of these companies. Okay, so so what are the things that you have basically? So you have the big data. So, for example, the search engine has 10 to the power 10 pages, or social networks have 10 to the power 9 nodes and 10 to the power 12 edges, and then you have to do machine learning. So, you may have to do image classification on millions of labeled images. So, this is the ImageNet data set, for example, or you can do speech recognition on again thousands of hours of annotated voice data, or you can do machine translation, tens of millions of bilingual sentence pairs, and or something like you could try to teach an algorithm how to play Go, for example, and for that again you have lots of expert moves already available. Okay. So, this is the first characteristic. The second characteristic could be that you could have big models. Okay. So, so for example, the Light LDA model which was published, it had it is basically a LDA model, late Dirichlet allocation model, with 10 to the power 6 topics and 10 to the power 11 parameters. So, and basically it is seen that the more topics you add, the better performance you get in downstream applications. So, for example, ad selection or click prediction. Okay. So, and similarly, for example, the Disbelief paper from Google, they had 10 to the power 10 weights. So, they were training a deep neural network for image classification, and this is the order of parameters that you learn from the data. So, you have big data and you also have big models that you want to train from data, and the point here is that models are only going to grow bigger because still we are not matching. So, the human brain has something like 10 to the power 11 neurons and 10 to the power 15 connections. So, we are still not matching the size of the human brain. So, the number of parameters that the human brain might have. And to handle, of course, all this big data and big models, we need big compute facilities. So, we have now cloud computing, we have large number of servers. On the other hand, we have highly parallel computers like GPUs, which can execute simultaneously instructions on thousands of data points in one clock speed, and then you can have clusters of GPUs. So, these are very popular now in compute hungry systems like deep learning, etc. And then there are other kinds of things like FPGA farms, your Raspberry Pi kind of devices. All of these could help you speed up and parallel, rather speed up computation in a distributed or parallel manner very fast. Okay. So, so this is one reason why you need distributed machine learning, or so in order to train for all the scenarios that I just described, you need to have distributed algorithms for machine learning. Okay. Now, I am going to describe another somewhat orthogonal scenario. So, in the previous scenario, the data was coming to a big company, and then these companies are processing them in a so the distributed computing is required mainly because of the large scale of data. Okay. So, the other paradigm of computing, which is called edge computing. So, in edge computing, the idea is that our devices are becoming more and more smart. So, now your cell phone has as much processing power as your laptops would have even 5 years back. Okay. And if you look at other devices like refrigerators, TVs, cars, etc., all these devices are having large amount of compute facility on board them. So, the idea is that can we put some part of the computation, and all these devices are collecting data, and many of these devices are actually running machine learning algorithms. So, for example, your cell phone is running a speech recognition algorithm, it is probably running many other machine learning algorithms. Okay. So, so the point is that can we have a machine learning architecture which is truly distributed rather than centralized, so that much of the computation can happen on edge devices. So, I will go into this use case of intelligent transportation. So, basically what happens now is that you have lots of devices. So, we are in the era of Internet of Things. So, we have lots of connected devices and intelligent connected devices, and these devices are collecting data, and they also have processing power. So, for example, your car has a computer in between. So, and it also has camera, it has LiDAR, it has probably some proximity sensors, it has a GPS receiver, and all these things. So, that it can sense your position, it can see whatever the things that are around you, it can create a map of the terrain around you, and so on and so forth. So, all these things can be useful in, for example, learning a system which will make the car drive by itself. So, this is the idea of autonomous vehicles, that all these sensors, they collect data, and then we analyze this data, and then we use some machine learning techniques to try and predict, for example, what should be the steering angle, what should be the throttle, should you brake, etc., etc. Okay, so this is one application. Another application could be monitoring or surveillance application. So, nowadays, as you know, there are CCTV cameras everywhere. So, for example, in shopping malls, in public places, in roads, etc. Okay. And for example, one application could be that can we monitor or can we do traffic forecast. Okay. So, can we say using cameras mounted near different junctions, almost all road intersections now have cameras. Okay. So using those cameras, can we predict or can we monitor the amount of traffic that is flowing through, and then maybe we can forecast the traffic and we can do route recommendation. Okay. So, these are all machine learning, these systems use machine learning algorithms. So, as I have already told that autonomous cars contain all these kind of data. So, as you can see, the Google self-driving car gathers around 750 megabits per second. Okay. So, this is a lot of data that the car is collecting. Okay. So, the current model of training is that the car collects this data and it is in a offline mode. Okay. So basically what happens is, in the training phase, the car is asked to collect a lot of data. So, it collects the data from these sensors and then it also collects the human driver's feedback. So, how much is the human driver braking, what is the steering angle, is it going left or right, and all these things, all these data it collects, and then that data is sent to a system where we train the machine learning models, and then the machine learning models are deployed to the car. Okay. But as you can understand, so all these vehicles are connected to the cloud. Okay. So, or at least in the future it is expected that the vehicles will be connected to the cloud. Okay. And the question is, can we transfer this kind of data in real time, or at least one should not have to segregate out the training and the testing phase for autonomous vehicles. So, as you drive your car, so the autonomous vehicle should be able to learn how to drive the car, or so that is the idea. Okay. And so this is a form of distributed machine learning, as you can understand, because there are many autonomous systems running, each one running on one of the cars, and then each one of these systems, they send the data to maybe a cloud in a real time manner, and then on the cloud the models get retrained or readjusted, and maybe there is a slight variation in the way you prefer your car to be driven than somebody else, then maybe that or maybe there is a difference between how the traffic is in city 1 versus city 2, and maybe you want to drive the car somewhat differently in 2 different cities. So, this updated model may be deployed in the vehicle accordingly. Okay. So, this is another form of distributed machine learning that we will see more and more often in the future. Okay. So, this I have already described. So, this is some computation. So, basically the computation shows that we need large amounts of compression of the current data, because the rate at which the data is currently connected, it goes to about 390 megabytes per second, okay, whereas we should probably aim for something like 10 megabytes per second of transfer, not more than that. Even that is actually high. So, then the question is, can we do this compression using machine learning tools? So, then the machine learning algorithm actually decides which machine learning algorithm which is running on the card actually decides which parts of the data to send to the cloud and which parts of the data not to send. Okay. So, so of course, there are many other scenarios where you need distributed machine learning. So, I have just described two scenarios which are very important in today's world. So, given these scenarios, what are the architectures that we can use to do distributed machine learning? So, the first architecture, which is now the most commonly used architecture, which is the one also we will be describing most in this course, is the data centric architecture. So, the data centric architecture is mainly for the use case of training over large data. So, training a machine learning model over large data. So, basically the idea here is that you split the data over multiple machines, okay, and the model parameters that you have are replicated over all the machines, and then you compute the updates to the model on each machine based on the local data that you have on that machine, and then you update the parameters on this machine, and then you communicate the updated model or updated parameters with the other machine. So, you synchronize with the other machines either via a central machine or via each other periodically. So, periodically you sort of synchronize this data with each other. Then the second approach, which is still kind of it is being researched on, and in certain cases it is very important, is called the model centric approach. So, this is the situation where the model that you are trying to train is very large model. So, so what happens is that data is accessible to all the machines. So, whatever machines that you have, you want to distribute the training of model over. So, the data is accessible, all the data is accessible from all the machines, but the model parameters are now split over different machines, okay. And the idea is that single machine updates models, only a subset of model parameters on itself, and basically, so the single update spans over multiple machines, and in this case basically periodically you synchronize the parameters which are not updated in this machine from other machines. So, this is the second view of distributed machine learning, or second way of doing distributed machine learning. The third way is that your data itself comes in a graph. So, basically you train the model over large graphs. So, your data itself comes in a graph. So, for example, it could be the web graph, or it could be a large protein-protein interaction network in bioinformatics, and then basically the data is partitioned according to the nodes of the graph, okay, and the computations happen on the nodes of the graph, and basically the operations on a vertex use the transforming data in the scope of that vertex. So, only the vertices which are connected to this particular vertex are able to update the, or rather affect the computation that happens in this particular graph. So, one example could be page rank computation for or there could be many other examples like statistical relational learning, etc. Also where the graphs are important, or the input, there are large input graphs which are important for the underlying machine learning model. So, typically the data centric training, one would use either MapReduce or Spark. For model centric training, typically one would use something like Disbelief or parameter server or Petium. So, these are basically all these are some kinds of parameter server yeah. And for graph centric computation, one might use something like Pregel or GraphLab, which are basically graph based computation framework. So, this is the difference between data parallelism and model parallelism that we have already discussed. So, here you can see that in data parallelism the data is partitioned, and in model parallelism actually the model parameters are partitioned, and accordingly your update strategy and synchronization strategy changes. Okay. So, up till now we have we have discussed the parameter for big data computation, or rather scalable data mining, which is Spark, which is, as you can think, that it is a data parallel or it is more suited towards data parallel computation. Okay. I will describe now another framework which is somewhat similar to Spark, but in its design, but it is very it is much more suitable or much more widely used in machine learning and especially in deep learning. Okay. So, this framework is called TensorFlow. So, the basic idea here is that you have tensors which are n dimensional arrays, and then the process of learning or the algorithm of learning is about flow of tensors from one node to another in a graph. So, if you recall, you also had a computation graph in Spark, where each node was a RDD and data would flow from one node to another as you the computation progress. So, here also the understanding is same, except that the data that flows from one node to another is a tensor. Okay. So, so just to give you an example of how this works. So, you basically have in a neural network a situation like this, where you have a set of input layers here, and so you have a set of input layer which are multiplied by these parameters w, and then you get the output layer. And given many examples, you want to compute this output layer w. So, the way this is, so this is how you would mathematically represent the network. So, you will have, you can compute A1, A2 and A1, B1 and C1 from, so these are the intermediate computation at this node, at this node. So, these are the intermediate computation at this node, and this is the input, and when you multiply by w you get this, and then you apply this ReLU function to get the actual output. Okay. Now, this you can do in TensorFlow like this, that you can define the input as x, this parameter as w, and then you can compute y, which is tf.matmul x comma w, and then you can compute this out, which is the output. Now, so the first thing is that how you define tensors. So, you can define two types of tensors. The first type is called variable. So, these variables are tensors which store the state of the current execution. Okay. So, for example, in this case the w is a variable because it is the parameter which will change as your training algorithm progresses. So, it will in some sense store the state of your computation as your learning algorithm progresses. Okay. Okay. So, if you write a code something like this, which is basically encoding the computation that we just said, then you notice that it is defining this kind of a graph. Okay. So, the node of these graphs, unlike in case of Spark, in this case the nodes are actually the operations. Okay. So, there are the input variable nodes, and the most of the nodes in this graph are computation. So, this is the computation matmul and this is the computation ReLU. Okay. And to this node, and the data that flows from one node to another is a tensor. Okay. So, from this node to this node, basically the tensor x will flow, and this node to this node the tensor which is stored in this variable will flow, and then some computation will be done and the resultant will flow to this node, and so on and so forth. Okay. So, so after you define the graph, you have to run the graph. So, you basically define a session. So, one way to think about the session is that this session is actually a graph. Graph is the computation itself plus the data that you provide to the graph, and then you start the session. Okay. So, this is the, so you define a session and then you can run a graph in TensorFlow using a session. Okay. Now, what you have to do is, now you have to provide the data. Okay. So, how you provide this this data x. Okay. So, first even before the data x, so you have this variable w. So, if you recall, this was the variable w that we defined. Okay. Right now, the w is just an empty node. So, there is no data here. So, first you have to give that data. So, that is done by initializing the variable. So, you can, for example, in this case randomly initialize the variable w. Okay. So, that is how you provide the data to w. The second thing that you need to provide is you need to provide data to x. Now, this x is different from w because it is not storing the state of the computation, rather it is fixed. It is a piece of data that you are providing from outside. Okay. So, this kind of data is provided using what are called placeholders. Okay. So, and this is how, so you define first x as the placeholder, and then you can feed the values for the placeholder as you run the session. So, this is the statement for feeding the value of the placeholder x as you run the session. And this is how the whole computation is done. And so as we shall see, or rather we will not go into detail of exactly how a training is done. So, TensorFlow provides also many other things, like it provides optimizers and it provides gradient computation, etc., so that you can very easily train this kind of model. Okay. So, we just refer to a comparison of how these systems perform. So, this is 3 systems. First one is Spark. So, the comparison is between 3 systems: Spark, TensorFlow and MXNet. MXNet is also an open source deep learning system, which is especially designed for distributed computation. So, this result is overtraining of a single layered neural network using the MNIST data set. So, this is a standard data set in machine learning, and you can see. So, what we are showing here is the CPU utilization. So, the first group, so this group corresponds to Spark. So, these are 3 types of networks with Spark. This group corresponds to TensorFlow and this group corresponds to MXNet. And what you can see is roughly the CPU utilization is slightly lower for TensorFlow and MXNet and slightly higher for Spark. This is because the Spark is implemented in Java and that has its own overhead, whereas both TensorFlow and MXNet are implemented in C++. Same pattern follows when we try to plot the memory utilization. So, Spark uses much more memory followed by TensorFlow and MXNet uses much less memory. But you see now when we look at the scale up, so on x axis for each of these Spark, TensorFlow and MXNet, now we are showing the number of so the scale up as the number of workers. So, the first bar is for 3 workers, the second bar is for the first one is for 1 worker, the second bar is for 3 workers and the last one is for 5 workers. On the y axis, what we are showing is how many images or how many training images is this system able to process per second. Okay. So, we see obviously if we give it less number of workers, it will be able to process less number of images. So, that pattern we always see. So, it is always increasing for. So, this one is for Spark, this one is for TensorFlow and this one is for MXNet. Now, what we see here is that the scaling of Spark is much better. So, as the number of workers increases, Spark system is able to scale much better than the other 2 systems. This is because Spark is more specifically designed for distributed computation. So, even though TensorFlow and MXNet can also perform distributed computation and they are in fact much faster in case that you do single node computation, but as the number of nodes increases, your Spark becomes somewhat faster in scaling. So, this you see also in the network utilization. So, here now we are showing the network utilization for in the y axis for the same set. So, you can see that Spark utilizes much less network compared to TensorFlow or MXNet. Okay. So just to conclude, we have seen two cases where distributed machine learning is very important, and we have seen the three possible architectures in which you can design distributed machine learning algorithms. We will see some specific algorithms in the following lectures, and we have seen some platforms like Spark and TensorFlow, and we have seen some comparison. So, basically what we have seen is that Spark computation is, or Spark platform is more designed for distributed computation, whereas TensorFlow is more designed for training machine learning model in a fast manner. So, these two have their own advantages. Both can do both, but they have their distinct advantages. And also we have seen that the underlying philosophy of both Spark and machine learning is to actually have computation graphs. They have different connotations on the computation graph, and they have different constraints. So, for example, in the Spark the computation graph is a directed acyclic graph, but in TensorFlow that is not the case. So, these are the two main differences between Spark and TensorFlow. So, for example, in Spark you have a DAG as a computation graph. So, you have a directed acyclic graph, whereas in case of TensorFlow you need not, your graph can have cycles. And the second difference is that in Spark the RDDs are immutable, whereas in case of TensorFlow you can see that you can have variables. So, these variables are actually mutable quantities. So, which basically means that TensorFlow cannot support something like fault tolerance and things like that, but on the other hand it is more suited for machine learning computation. So, these are the references. The comparison is taken from this particular paper, and some of the things are taken from Introduction to TensorFlow.